Dear learners, I welcome you again. Last time we considered some quantities using describing bodies that are undergoing rotational motion. We considered the angular displacement, look at angular velocity, angular acceleration, and compared with their linear counterparts, which you know before now: distance, velocity, acceleration. Today we are moving further and looking at some other quantities, such as the angular momentum, torque, and we also consider the relationship between the angular momentum, torque, and the equivalent in the translational motion. And I believe the comparison is to get you familiarized with this concept so that you can easily recall them while handling numerical problems. First, we look at angular momentum, which is the physical quantity that measures the rotary inertia of the body. And that body be a system of objects, system of particles. So it's the quantity that measures the rotary inertia of the body in motion about an axis. That's angular momentum. Angular momentum deals with a body that is going in a linear motion, straight line motion, from one point to another in a straight line, translational motion. But angular momentum deals with object that is rotating, object that is in rotational motion. And you will see that if you check the right hand side, the image there, the figure, the M is the mass of the object marked blue. That's blue circular shape represents an object that is going along the circular path. The red dotted circle represents the path to which that body is rotating. And the momentum, angular momentum of that body is a function of the linear momentum and the radius of rotation. And you can see they must be perpendicular to each other. And the perpendicular, that's why we have the cross product. This angular momentum, which is represented as capital L with that arrow, indicating that it is a vector quantity equals to the cross product of two other vectors, which is the radius of rotation, which was perpendicular. That's the essence of that being the vector quantity. It was perpendicular to the linear momentum, represented as P, which is also acting in a particular direction, a vector quantity likewise. The angular momentum is defined as the product of linear momentum of the rotating body and its distance from the axis of rotation. We still see that on the next slide. If we have this formula, cross product of R and P, the axis of rotation, the distance, the axis of rotation, and the linear momentum. If the maximum angular momentum are to be obtained, if we are to obtain the maximum angular momentum, then it must be perfect perpendicularity between these two parameters, R and P. And in that case, for R, we have RP sine the angle, which we have stated as psi. Angle here, psi. So we can go further. We see that R cross product P, RP sine phi, for phi, which is 90. When you have the perfect perpendicular relationship between R and P, phi is 90 degrees and sine 90 is 1. So any angle lower than 90 degrees between the two. Let's assume now that the force acts such that the momentum is like this. Then this angle is less than 90. That means the angular momentum will decrease. That's what this means. Again, like this, it will further decrease because the angle is getting smaller. And by the time you now have a momentum that is acting, you have a momentum like this due to the force acting on the object. At that point, when your phi is almost equal to 0, then that means there won't be angular momentum. Then that body will not be able to rotate at all. There won't be rotation. So maximum angular momentum is obtained when R and P are perfectly perpendicular. Again, we have our L equals R, then cross product of mv. Momentum P is mv. So when we have P, we put our mv there. And because m is a scalar quantity, you can break it outside the bracket, and you have the cross product of R and V, which is mrv sine phi, just like we have for rp2. Because the angle for a maximum angular momentum, the angle between R and the action of the body, the momentum, or the velocity of the moving body, must be perpendicular to each other. That means we have sine phi, which will be 1. And also, V is a product of the radius of axis of rotation and the angular velocity. To substitute it into this expression, then we have the next expression, which is mr squared omega, which is expressed as I omega. I is mr squared and is called the moment of inertia for the body. Moment of inertia of the body. So angular momentum is also defined as the product of the moment of inertia I and the angular velocity omega, and it is measured in kilogram meter squared per second or Newton meter second. So you can present the unit in kilogram meter squared per second or Newton meter second. Remember, Newton is kilogram meter per second squared. So if you substitute how you have Newton, put kilogram meter per second squared, then you also put it in the second expression, you also obtain kilogram meter squared per second. Let's go to the next slide. We have our torque. Torque is also another quantity, and the equivalent of torque in linear motion is force. Torque is the physical quantity that measures the effectiveness of the force applied on the body in producing rotation of that body about an axis. So how effective is the force in causing the body to rotate? That's torque. And that means the effectiveness of the force relies on the angle at which that force is acting on the body. Very important. The effectiveness depends on the angle. So torque is a function of the angle at which the force is acting on the body. We see that as we go on. Still refer to that image. The torque about an axis or pivot or fulcrum is the moment of a force acting on a single particle at a point P with a point vector R from the origin O. So the moment of a force, that's what torque is. The moment, you call this secondary school, when you are taught moment, you have a fulcrum. So fulcrum, assume the point O, the center of the axis of rotation is our fulcrum or pivot. Then you have an object and a force acting on that object. Then we have a position vector from this is the origin. So the force is acting on a single particle from the position from the origin. We have for her. So the moment, remember moment is what? This, that's there. That's moment. So the moment of a force that acts like this is the torque about the axis. So, and like I said, the effectiveness of torque is a function of the angle at which the force is acting on the object. For example, the force may act like this. If it's acting like this, the torque will not be as effective. The force will not be as effective as when it is perpendicular. But when it's acting, you push it like this, it also will not be as effective. If the force is applied like this, in a straight line, parallel to the position vector, then there won't be any rotation at all. There won't be any rotation at all, no matter the amount of force. And we'll see shortly why that is. I'll describe it further. So unit of torque is Newton meter and can also be expressed in kilogram meter squared per second squared. Look at that image to emphasize what I have. You could see if the force F1 is acting perpendicular here, where here means that this angle means that the angle between the action on the mass, the body, is perpendicular to the position vector, to the radius of axis of rotation, then you have phi to be equal to 90. And at that point, sine 90 is equal to 1. So you have a maximum torque. So your torque is the force is most effective. The highest value of torque. Okay, so here we have for F1, we have T tau. Torque is written as tau. It's not T, tau. Let me rewrite it. It's written as tau 1. Now, if you have the force acting just like F2 acts, in this case now we have a higher angle. It is not perpendicular. You see, it is not perpendicular and it's not equal to 90 degrees. At that point, our theta is greater than 90 degrees. And if greater than 90 degrees means greater than 90 degrees. That means your sine phi will not be equal to 1. It will be less than 1. Sine phi will not be equal to 1, but less than 1. So at that point, we have your T1, it will be your T1 will be greater than your tau 1, torque 1 greater than torque 2. So F1, force applied in the position of F1 will give higher torque, more effective than F applied at the position of F2. The force applied at the position of F2, which will give a lower torque. Likewise, in this case now we have also this angle, which is much lower than 90 degrees. Let's assume it is 30. So in this case, let's assume that in this case we have psi is equal to 30 degrees, which is far less than, and that's less than 90. That's less than 90 degrees. You have it. Sin 30 degrees will be 0.5. So what does that mean? That means we have 0.5. That means T3, the torque due to the force applied at point 3, F3, will be half of Rf, which will be half of T1, of tau 1, sorry, of 1. So you can see that the most effective rotation is obtained when you apply the force perpendicular to the radius of axis of rotation. That is, applying the force at point F1. So you must remember that the highest torque is obtained when R is perpendicular to F. So torque is described as the physical influence that tends to rotate the body with mass. It is equal to the rate of change of momentum of the object. So again, tau is equal to the rate of change of momentum. Remember also from secondary school that force is rate of change of momentum, and that's linear momentum with time. Change of linear momentum is what? That's m, change in m, or let me see, change in, or let me write it this way. That is change, that is our m will be minus mu over t. That's for the force. Likewise, the equivalent rotational motion torque is the L, that's the linear angular momentum over time, rate of change of angular momentum with time. In that case also, we can express it further, which will be change in I final is minus I initial angular velocity over t. Do that. And recall, you can make actually formula. Recall that this change omega f minus omega angle of I over t. We know that, and you may recall that theta is equal to omega t, and that means omega is equal to theta dt. So you can put it here too. We can obtain several formulas. I theta 1 2 over t squared. You can do that. So on and so forth. We still see how we derive this expression. Now, as a body is rotated, as a body goes round in rotational motion, what happens is the energy is expended by the body. The body is doing work. It's working against friction. Okay, going against friction, maybe you have friction, you have to be going in here, or friction with the surface the body is making contact with. Energy is expended. You can now obtain that energy expended or the work done by the body. Recall that for translational motion, work done is the product of the force that causes the body to move from one point to another and the distance covered by the body. That is F dx. We can integrate from the starting point, which is S of I, to the finishing point, X subscript F. We integrate, then we have the work done. Likewise, for rotational motion, the work done will be the product of the torque causing the rotation and the angular distance covered by as the body rotates. Okay, so the change in the angular position of the body, the theta, the product of the torque and the change in angular position of the body, the theta. We integrate it from the initial position, angular position of the body, to the final angular position of the body. If you integrate that, the torque tau is a constant. You bring it out, you integrate, and for integration, you have the final expression. Tau change in the angular displacement, that is tau open bracket theta subscript F minus theta subscript I, that is change in the angular momentum, which can also be expressed as tau theta. So that's the work done. That's the work done. You can also obtain the power, that is those are what each parameter stands for: the torque, the angular change in angular displacement, and you can now also obtain the power of rotating body, which is also very relatable. You can obtain it from what you have for transitional motion, or you can also obtain it directly from what you have for work done in the rotating body or by rotating body. From translational motion, remember, force is force times velocity. Okay, so the force, velocity, and velocity is the product of the radius of the axis of rotation and the angular velocity. And again, this, what I'm putting into parentheses, the cross product of force and R gives you your torque. So you have your power. Or you can also work with this. Since power is known to be energy expended over time, rate of energy expended, that's what power is. Rate of energy expended, that is work done over time, or energy expended over time. And from what we obtained earlier, the work done or energy expended is tau theta divided by time. We have tau theta over t, and recall that theta is equal to omega t. So the tau, your answer power is tau omega. That is the product of the torque and the angular velocity. So we also look at what each parameter stands for. Again, tau is the torque causing the body to rotate. Omega is the angular velocity of the rotating body. R is the radius of the body's circular part. That is the radius of the axis of rotation, or radius of rotation. Also, we can also obtain kinetic energy of the rotating body. As the body rotates, it possesses kinetic energy. It's in motion. Also, from translational motion, Ke is equal to half mv squared. Equivalent, V is R omega. So just substitute, and you have I omega squared. If you substitute R omega then squared, you have R squared omega squared. And mr squared said can be taken to be the moment of inertia. So you have half I omega squared. Again, m mass is equivalent to the moment of inertia. Remember, mass is a measure of inertia in linear motion. So moment of inertia, then linear velocity is also covariant of angular velocity. So half mv squared for linear motion, half I omega squared for rotational motion. You have what each parameter stands for also. When I moment of inertia rotating body, and omega is the angular velocity of rotating body. Now is the radius of the body circular part, or radius of rotation, and then is the mass of the okay. Newton's second law, you know that that's Newton's second law, and recall that F is equal to mr. Remember F is ma, mass acceleration, and our linear acceleration is a product of r and angular acceleration. Okay, so that means another expression for force is this. Also, recall that tau, the torque, is a cross product of r and f, radius of radiation and the force. Okay, so if you have that, you have your MRA, substitute it here. Because remember we said for a perfectly perpendicular force with the axis of rotation, you have RF since sine phi you got to 1, sine phi is equal to 1. So you have substitute where you have your head. Here you have substitute MR alpha. So you have R in bracket MR alpha. If you have MR squared alpha, you have, remember again, call that MR squared is moment of inertia. So you have I, then you have your alpha. So this is that formula to use to obtain the torque. That formula to obtain the torque. Now, in addition, if multiple number of torques act on the body, maybe due to different forces, if multiple number of torques act on the body, then the net torque acting on that body is the summation of the individual torques that act on such a body. So I will just calculate the torque for each body. Then do that torque. In this case, look at it, for example, let's assume you have a body. You have a body, and that body is the axis of rotation. It's rotating on this axis. It's rotating on this axis. But we have different masses, different distribution of different masses. From the distance from the axis of rotation, R, you can know this F can act, and that R, this can act, and that R, this can act, and that R, this can act. So you obtain the torque at each of the torque acting on the body. Then you sum up to obtain the total torque. Comparing the quantities, linear and rotational, so I can easily get used to them. The equivalent of mass, the linear, the rotational motion, the equivalent is moment of inertia. Linear motion, kinetic energy is half mv squared. We replace m with moment of inertia and b with omega. Linear velocity, angular velocity. Do you get it? Force, replace with torque, and s, replace with theta. Very straightforward. MA, you have first you have MA, here we have this. So when you have M, again I, when you have the V, the omega, B is linear velocity, omega is angular velocity. T, you see, when you have linear momentum, angular momentum L. So it's straightforward. You can work with it, and you discover that they are very simple. Right? If you have clarifications, again, as I usually say, you have questions, please put them in the comments, and I will do my best to respond to them. Likewise, subscribe to this channel and share with others so that they can also benefit. Wish you success in your academic job. God bless you.